In this video, we are going to be talking about the Kirchhoff's law. Okay, now the Kirchhoff's law is a very useful law in the current electricity. It is very useful in solving complex problems. So where Ohm's law can no longer be applied, majority of the time, Kirchhoff's law will come into place. Okay, now there are basically two laws. We have the first law and we have the second law. Now, the first law is called the junction rule, and the second law is called the loop rule. Okay. Now, using the series of explanations and having diagrams, we should be able to understand the Kirchhoff's law. Okay. Now, mind you, you should already have an idea of Ohm's law. V equals IR, the general formula. If you don't, the videos on our playlist, you should try and watch those videos. Okay, to gain an understanding on Ohm's law. Now, the first law here is the junction rule. Now, this junction rule is also called the KCL. That is the Kirchhoff current law. Okay, the Kirchhoff current law is also what we call the junction rule. Now, what does it state? It states that the total current that is entering a junction is equal to the total current that is coming out of that junction. Example, let's say we are having a junction. Okay, a junction is simply where one or two wires meet. That is where a connection is made. Okay, let's say we are having a junction and we are having one wire, okay, connected to two other wires like this. Okay, now if the wire here carries a current I1, for example, okay, and the wire here carries a current of I2, and this one carries a current of I3. This one is in this direction, this one is in this direction, and this one is in this direction. So Kirchhoff rule, okay, or the KCL rule, which is also known as the junction rule, is saying that if I sum all the current that is going into the junction, which is I, okay, the sum of all the current is I1, okay, it is going to be equal to the other current that are leaving the junction. That is, total current entering the junction should equal total current leaving the junction. So I1 is simply equal to I2 plus I3. Now, this equation is correct because we can see the direction of the current in the diagram. Let's say we change it, okay, let's say we make a little change, and then this current is going in this other direction, and then this current is going into the junction. You notice that this is the only one coming into the junction, and as it gets here, it's kind of split into two parts. One goes to I2 and the other one goes to I1. It means for a diagram like this, it now becomes I3 is equal to I1, which is leaving the junction, plus I2, which is leaving the junction. So what is the rule? All you have to do is take note of the current that is going into the junction, write it out, and then equate it to the current that is leaving the junction. That is I1 in this case, and also I2 is leaving the junction. Now, this KCL or the junction rule is also called the current rule, like I said, okay, KCL, that is Kirchhoff current loop, and it's also based on the conservation of charge. Okay, so if you are being asked in an examination which of the Kirchhoff rules is based on the conservation of charge, it is what now? The KCL. Okay, it is that easy. Now, how about the loop rule? The loop rule talks about the voltage in a circuit. Now, it is also called the KVL. Okay, that is the Kirchhoff voltage law. This law is saying that the algebraic sum of potential difference of voltage, okay, across a loop is equal to 0, in the sense that whenever we take the net sum of the potential difference across a loop, it is always equal to 0. Similarly, with the junction rule, whenever we take the algebraic sum of the currents, okay, at a junction, it is equal to 0. What do I mean? Now, I can as well rewrite this equation 3, to equal I3 minus I1 minus I2, and this is equal to 0. Now this is the algebraic form. Why is it? Because we are taking account of the directions of the current, in the sense that since this is the one going into the junction, we can make it positive, and anyone that is going away from the junction, it becomes negative. So we're having I3 plus negative I2, which is same as minus I2, plus negative I1, which is same as what now? Minus I1, and that is equal to 0. Okay, so we can as well state junction rule or KCL as the algebraic sum of currents in a junction is equal to what now? 0, which is what we are having here. Okay, now how about the KVL? Bring your mind back to the KVL. The KVL, which is the Kirchhoff voltage law, or the loop rule, applies to when we are having a loop. A loop is simply a closed section. For example, if we're having something like this, okay, what we're having here is a loop, okay, because it is a closed section. It could be rectangular, triangular, circular, or any shape. As far as it is closed, it is what now? A loop, and we can apply the Kirchhoff voltage law, which is saying that the sum of the voltage in a closed loop is equal to 0. Now that is not also Kirchhoff law. It is important that we take note of everything we're having on this other side of the board, okay, to get a very good understanding on what Kirchhoff's law talks about and how we can solve problem on it. Okay, now here it says that directions must be assigned to current and element in all the branches, okay, of a loop. If the wrong direction is chosen, it will be negative and its magnitude will be correct. Now what do we mean by this? Whenever we are going around a loop, okay, in this case, this is what now? The clockwise direction, okay. This clockwise direction, we are assuming that the current is flowing through the circuit like this, okay. By assuming this direction, which is the clockwise direction, we are assuming that the current is flowing through the loop like this, of which in real sense we cannot even tell, we do not know, okay, but we are assuming. But when we now solve and we find out that if, for example, the current here is I1, okay, after assuming that the direction here is the direction that the current is flowing in the circuit that is given to us, and then we solve, when we discover that, for example, if the current here, which is supposed to be going in this direction, okay, I1 going in this direction like this, okay, is negative, if the value of I1 is negative, this means I1 is supposed to be in the other direction. So if I1 is negative, it means it is simply what now? In this other direction, its value will be the same, only its direction is going to change. Okay, so I'll read this again. Directions must be assigned to currents and elements, which is the direction you just took, which could either be clockwise or counterclockwise, which is the same as anti-clockwise, depending on the person solving, okay, in all the branches. Now we'll talk about branches in an electric circuit. These are the branches, these lines, these are the branches, okay. An element, now the elements could be resistors, capacitors, okay, of which resistors are the most common. Of course, in these diagrams above, you can see them. These are what now? Fixed resistors, okay. Now if the wrong direction of a loop, if the wrong direction is chosen, it will be negative and its magnitude will be correct, okay. So the only thing that changes is the sign, and you are going to know, okay, because the sign will simply tell you that it's supposed to be in the opposite direction, okay. Now next, we are saying here a clockwise or anti-clockwise direction must be chosen for going around the loop. So we are either going to choose a clockwise direction or an anti-clockwise direction, depending on you, okay. So whichever one works best for you, all you have to do is what now? Pick one. It's a must. It either has to be in the clockwise or in the anti-clockwise direction. And then lastly, identify the unknowns and use both rules to generate equations which can be solved simultaneously. So now these two laws, after they've been applied to a problem, what we do is we generate a series of equations, okay. We are not then going to identify what we have to solve for, which could be either the current through a particular resistor, okay, the current through the whole circuit, or the voltage, okay. Immediately we identify what we have to work with or what we have to solve for, all you have to do is create a simultaneous equation and then apply the principles of solving simultaneous equations to get your answers, okay. So here are the steps. Assigning the signs, okay, and the direction as well, which could be clockwise or anti-clockwise. Get your equations and then solve simultaneously, okay. Problems are definitely going to be solved in our next video. to gain a more or a better understanding on how to deal with the Kirchhoff law. Okay, now here are also 4 diagrams that we must talk about. They are important. Okay, now it is important to take note that current moves from a higher potential difference to a lower potential difference. In this case, you can see that the current is moving from A to B. It means that the potential difference of A is higher than the potential difference of B. Current must always flow from a higher potential difference to a lower potential difference. So if we are moving in this direction, we are moving from positive to negative. It means the voltage across this resistor is going to be negative, in the sense that V is equal to minus I arrow. Simply because current, we can see in the diagram that current is moving from here to here. But if we do not know that current is moving from here to here, we'll assume anyone. We can choose to write minus I arrow, or I can choose to remove the negative sign, becomes I arrow. In the end, after solving, if we get a negative, it means that the direction we pick is in opposite direction. If we get a positive, it means the direction is in the direction that we assumed. Okay, so in this case, current is moving from A to B. It means A is at a higher potential difference, B is at a lower potential difference. Okay, that means the voltage across this resistor is what now? Negative. How do I mean? Okay, now this also means that there is a potential drop, that is a loss in potential difference. The resistor has what now? Dissipated some energy. Hence, the potential difference at this point is now what now? Reduced. Now look at this diagram. Okay, now we are saying that in this case, current is moving from B to A. If current is moving from B to A in this diagram, and the direction we want is also from B to A, it will be negative, just like in this first case. Current was moving from A to B, and the direction we took was also from A to B. That is why our answer is negative. But in this case, current is moving from B to A, and the direction we also want to take should be from A to B. It's always from A to B we want to take, not B to A. But then current is moving from this side to this side. It was given in the diagram, so we know it was moving from here to here, which means B is at a higher potential difference than A, or A is at a lower potential difference than B, since current is moving in this direction. What next do we do? What will be the potential difference of the voltage across this resistor? In this case, the potential difference of voltage will be I arrow. It will be positive, simply because we are going from here to here. Okay, that is, here is smaller than this other part, because we are going what now? Against the current. So if you are going against the current, there is a positive potential difference, or there is a potential rise. That means V is equal to what now? Positive I arrow. Okay, why for this one? We are going in the same direction as the current, so it means what now? It will be negative. So you might as well want to take note as a shortcut that if you are going in the same direction as the current, your voltage will be what now? Negative. If you are going in opposite direction as the current, your voltage will be what now? Positive. Most persons might confuse this, thinking, since you are going in the same direction as the current, why shouldn't your voltage be positive and opposite direction should be negative? Okay, well, it doesn't work when we are having what now? Kirchhoff's law. Opposite direction to current is what now? Positive, and the same direction is what now? Negative. Now similarly for the cells, you can see we're having two unequal lines telling you that this is what now? A cell, okay, having an AMF. Okay, these guys are having an AMF. Okay, this is not a capacitor. For capacitors, we're having equal lengths in lines. So you can see here is negative, here is positive. Since here is negative and here is positive, what does that tell you automatically? Current always move from positive to negative terminal, right? It means current is flowing in this direction. Okay, so if current is flowing in this direction, we should be having a positive E. Okay, sorry, a negative E rather. Okay, positive, negative. So if you are going in this direction, okay, if you are going in this direction from B to A, okay, we are going to have a negative. But if we are going from A to B, we are going to have a positive, because we are what now? Having a potential increase. Or what did we take? Okay, at first we took from A to B and A to B. Okay, so let's take A to B. Let's take A to B. Okay, I want all our directions to be from A to B. Okay, to make it easier, all our directions to be from A to B. So if I'm moving from A to B, we can see that we're moving from negative to positive. That is an increase. Okay, so we're going to assume the potential difference of the EMF here to be positive. Okay, now in this case, here is positive, here is negative. It means current is flowing in this direction. Okay, we're moving from A to B, which means we are moving from a positive to a negative. Okay, so that means we are going to have what now? A negative EMF. It is that easy. Okay, now in our next video, we'll be solving some series of problems on the Kirchhoff's law Okay, do well to like the video if you did learn something, and put your question in the comment section if you have any. Okay, and then don't forget to hit the subscribe button and click on the notification bell so that when a new video has been uploaded, you'll be one of the first two persons that will get notified about it. Okay, see you in the next video. Bye.